Welcome to this lecture on sequences and series of functions. Today we are going to explore a fascinating and crucial topic in mathematical analysis, pointwise and uniform convergence. Imagine you are managing a restaurant and teaching chefs a new recipe. Some learn fast, some learn slow, but eventually they all get it. That is pointwise convergence. But what if a master trainer gets everyone to learn it at the exact same time? That is uniform convergence. Understanding this difference is the key to unlocking advanced calculus and ensuring our mathematical models do not break down. Let us dive in. Now that we have our chef analogy, let us look at how this works mathematically. In calculus, we often deal with a sequence of functions, which is simply a list of mathematical rules that evolve step by step. We want to know what final shape this sequence eventually turns into. If we freeze one specific point on the graph, the sequence of values at that exact location might settle down to a final target number very quickly. However, if we pick a different point, it might take an incredibly long time to reach its target. Because the speed of reaching the destination depends entirely on which specific point you pick, we call this pointwise convergence. This brings us to the rigorous mathematical definition of pointwise convergence. Conceptually, we want the distance between our moving sequence and our final destination to shrink to zero. The formula shows the absolute difference between the sequence function f sub n of x and the limit function f of x. We demand that this vertical distance becomes strictly less than a tiny positive number called epsilon. Here is the catch. This must hold true for all steps n beyond a certain threshold step capital N. In pointwise convergence, this threshold step capital N depends heavily on the exact location of x you chose as well as the error tolerance epsilon. If you move to a different x, you might need a completely different, much larger threshold step to achieve the same accuracy. Before we move on, let us see this with a concrete example of a sequence that converges pointwise but not uniformly. We are given the sequence of functions f sub n of x equals x to the power of n on the closed interval from 0 to 1. Our goal is to determine the pointwise limit function and investigate whether the convergence is uniform. First, we find the pointwise limit by fixing x and letting n go to infinity. We have to check different parts of the interval because the function behaves differently when x is exactly 1 compared to when x is a fraction less than 1. For any fraction strictly less than 1, multiplying it by itself infinitely many times drives the value to 0. Continuing with our example, we must remember that our interval also includes the exact number 1, which behaves completely differently. We have to evaluate that specific point separately to find the complete limit function. When we plug the exact value of 1 into our sequence, the situation changes dramatically. The number 1 raised to any power, no matter how infinitely large that power becomes, is always exactly 1. Therefore, at the very right edge of our interval, the sequence does not collapse to 0 at all. Instead, it stays stubbornly fixed at a height of 1. This means our final limit function is actually split into two completely different pieces, depending on where you look. This brings us to the final result for this sequence. The piecewise formula shown represents the final pointwise limit function we have just discovered. Notice that while every individual function in our starting sequence is a perfectly smooth, continuous curve, our final limit function is broken and discontinuous at x equals 1. This sudden, sharp break is a massive red flag in mathematical analysis. It tells us immediately that the convergence cannot possibly be uniform. If we try to put a tiny, straight error ribbon around this broken limit function, the smooth, unbroken curves of the sequence will always have to stretch across the vertical gap, meaning they will always poke outside the ribbon near x equals 1. As we just saw in the example, pointwise convergence can lead to broken limits. This brings us to a much stronger and more powerful concept, uniform convergence. In uniform convergence, the sequence of functions still approaches the limit function, but it does so at a guaranteed minimum speed for the entire domain all at once. Imagine placing a ribbon of a certain width directly over the final limit graph. If the convergence is uniform, there will be a specific step where the entire graph of the sequence fits completely inside that ribbon, and it stays inside for all future steps. The most important distinction here is that the threshold step depends only on the error tolerance, and it does not depend on the location at all. Now let us look at the mathematical condition for uniform convergence. Visually, this inequality looks completely identical to the one we used for pointwise convergence. However, the logical rule governing when we can use it is entirely different and much more powerful. Here, the absolute difference between the sequence and the limit is guaranteed to be less than the tiny positive number epsilon for every single point in the domain simultaneously. The threshold step capital N required to achieve this accuracy depends exclusively on the error tolerance epsilon, and it is completely blind to the location x. As the error tolerance is made smaller, the required step will naturally increase, but that single universal step will successfully trap the entire function graph within the error bounds all at once. To truly grasp this universal threshold, let us visualize it with a diagram. What you're looking at perfectly illustrates the ribbon concept of uniform convergence. The thick central black line is our final destination, the limit function f of x. The shaded blue band around it represents our allowed error margin, stretching up by epsilon and down by epsilon. Because the sequence converges uniformly, we can find a specific step where the entire red dashed line, representing our sequence function, is completely swallowed by this band. If the convergence were only pointwise, parts of the red line might stubbornly poke out of the band no matter how long we wait, because some points would take much longer to settle down than others. Now that we understand the uniform error band, let us look at a sequence that successfully converges uniformly. Consider the sequence of functions f sub n of x equals x divided by n on the closed interval from 0 to 5. We need to find the limit function and prove that the convergence is uniform. In this step, we are finding the pointwise limit by letting the step number n approach infinity while keeping the input x fixed. Because x is just a specific finite number chosen from between 0 and 5, dividing it by an infinitely large number completely crushes the fraction down to 0. Therefore, our final limit function is simply a flat horizontal line at 0. Moving forward with our proof of uniform convergence, we must rigorously check the distance between our moving sequence and our stationary limit function. We subtract the limit function, which is 0, from our sequence function, which is x divided by n. The absolute value bars ensure we are only looking at the positive vertical distance between the two graphs. Our goal now is to find the absolute maximum possible value of this vertical distance across our entire specified interval. We know that our input variable x is restricted to the closed interval from 0 to 5. Therefore, the absolute largest value that the numerator x can ever take is exactly 5. This brings us to the final step of our uniform convergence check. By replacing x with its maximum possible value, we create an upper bound for our fraction, which is 5 divided by n. Notice the most crucial detail here. The variable x has completely disappeared from our worst-case scenario expression. This means our maximum error depends only on the step number n. We want this maximum possible difference to be strictly less than our chosen error tolerance epsilon. By setting 5 divided by n to be less than epsilon, we rearrange this simple inequality to solve for the required step number n. This final result tells us exactly how to choose our universal threshold step, proving the sequence converges uniformly. So we have proven that uniform convergence holds for our sequence. This brings us to an important question. Why do we care so much about this distinction? In the real world of engineering and physics, we constantly use sequences of simple functions to approximate incredibly complex signals. If our approximation only converges pointwise, terrible things can happen. A sequence of perfectly smooth functions can suddenly converge to a broken limit, and you cannot safely swap the order of calculus operations. If you try to integrate a pointwise convergent sequence, you might get completely wrong answers. Uniform convergence is the mathematical safety net that guarantees the limit function will inherit the good properties of the sequence, making advanced approximation methods reliable. Let us summarize the key takeaways from this topic. Pointwise convergence means a sequence of functions reaches its target eventually, but the speed of arrival varies wildly depending on where you look. Uniform convergence is a much stricter condition, where the entire function approaches the target evenly and simultaneously, fitting inside a universal error band. While pointwise convergence can lead to broken limits and failed calculus operations, uniform convergence preserves continuity, integrability, and predictability. Understanding this distinction is an essential tool for safe mathematical modeling and advanced calculus. You now have a solid foundation in sequences of functions.